Okay, so today we're going to talk about the last type of t-test that we are going to do before we start doing analysis of variance. Now, surprise, the good news is there's really nothing new here today as far as tests go. There's no new questions, there are no new tests. So why are we having class? Well, we're going to think about some things in new ways, but the questions and the tests are going to be old. So today we're going to talk about variance a bit more, and we're going to see how variance differs for dependent and independent samples, particularly the difference between two samples. So finally we'll do some old tests to answer old questions in a different way. And we're going to call this new thing the paired t-test. But really it's just an old thing. Really just an old test. So keep that in mind. All right. Imagine we have some research question. Maybe some of you guys have seen some apps that they have for iPads and iPhones and other stuff like memory training exercises. So does that stuff work? Is there any benefit to doing that? So maybe we want to see if some type of memory training affects memory. If it does affect memory positively, then that might be a good thing to tell people to pay $4.99 for at the App Store. If it doesn't, maybe they're just wasting their money. It might be fun, so maybe it's not a waste of money, but if their intent is to improve memory, maybe it's not such a great idea. Now, we can take two samples to test this, right? Right? Can we test this with one sample? This isn't a methods class, but in intro we talked a little bit about methods. We talked about like experimental and control groups, right? You need something to compare it against. You actually could do a one sample test if you knew what the population memory score was. You could find some group, take a sample of people and train them, and then see if their scores differ. So I guess you could answer this with one sample. But if you wanted to do a two sample test, you could have like some type of control and experimental group, right? So our null hypothesis, this is an old null hypothesis. This is what we had last class, right? This is a hypothesis about the difference between means. The mean of the untrained minus the mean of the trained equals 0. Training doesn't affect memory, okay? This is an old question. We dealt with this last class. Let's say that alpha is going to equal 0.05 for the remainder of this lecture, since that's tradition. Now, we can sample both trained and untrained groups, right? There are two ways to address this question with two samples. One way involves independent samples. This is what we were talking about in last class. So with independent samples, like what would your two samples be? Anybody? Take one sample and do something. Take another sample and do something. What do? You can compare them, right? You compare their memory performance. And what needs to differ between these samples? If you want to draw conclusions about whether training has any effect. We're going to take one sample, we're going to take another sample, we'll compare both of their scores on some memory test. Okay. But if we want to see if training has an effect, what has to differ between our samples? One has to be motivated? Manipulated. What has to be manipulated?
Independent.
Okay, the independent variable, which is training. We need to manipulate training, right? So we need to take one sample of people that haven't been trained, and then a sample of people that have been trained, right? Or we can take one sample and not train them, and another sample and train them, right? So we can test a group that hasn't been trained, and test a different group, a different sample that has been trained, right? Now if we're randomly sampling, then our first group that we pick is going to be independent of the second group that we pick. right? This is why the logic behind doing an independent t-test, when you have two independent samples, right? Now we can also do this with a paired sample. How can we do this with a paired sample? Or with paired samples? What does it mean to pair? They depend on each other. So do you guys know Rakesh? It's pretty cool.
Yeah.
He's getting paired this weekend. He's getting married, right?
Yeah.
There's a pair, two things that go together. So we need two samples that go together. So how could you get two samples that go together? Previously, we took one sample, and then completely ignoring what we had in the first sample, we drew another sample, right? Now, if the second sample is going to depend on the first, then we're not really randomly drawing the second, right? There's some dependency. They're not independent. So one thing that we could do is we could randomly sample a bunch of people, test their memory, and then we could train them. And then test their memory again. Does that make sense? It doesn't have to be that way. There are other ways that we could do it that we'll talk about later on. But this is a very sort of easy, intuitive way. You get one group of people, you have them do one thing, you change something, you have them do something else, right? So we're going to take a sample of people, give them the memory test, train them, give them the memory test again. See if there's a difference, right? Now the question, this is still the same question. Is there a difference between the mean of trained and untrained? So the question is identical. All right, so imagine that we were going to look at one pair of scores. Now imagine that we took two independent samples. So I got a bunch of people, and then I got a bunch of people more. And I gave them the the memory test. And let's say that Mehmet, he didn't get any training, and he got a 47. And Aisha, she did get training, and she got a 53. Okay? So in my first sample, they didn't get any training. One of the individuals, Mehmet, got a 47. In my other sample that did get the training, Aisha got a 53. Now compare this with the situation where you have dependent or paired samples. Imagine that you have Ravza. So Ravza, before the training, got a 47. After the training, Ravza got a 53. So my question is, which of these pairs, these are both pairs, right? But these pairs are just sort of randomly thrown together. Whereas this pair is like a meaningful pair, right? So which pair provides more convincing evidence that the training worked? The paired samples. That's right. Why?
Because we can compare before and after. What's the difference?
And why does that help us? I mean, because this is still before and after, right? This is before training, this is after training.
Two of them are different, but here is the same.
These two people are different people. These two people are the same. Did you have something?
The sample size as well?
Imagine that we had the same sample sizes. And we're just looking at one pair here, just to try to figure out, does everyone sort of agree that this would be better evidence? I mean, this is not enough evidence. I would not be happy taking just one person and comparing them to two people. I would want a larger sample, right? But if I only had this data, I think that this is more convincing than that. So the question of why, Mehmet, as she said, and Aisha are different people. What do we know about different people?
They have different scores.
They have different scores, okay?
They have different abilities.
They have different abilities,
Different education.
different education, different perceptions,
Personality.
different personalities. Come on, hop in. Different gender. Wow. Yeah, Mehmet and Aisha, they are different genders. They come from probably different backgrounds. They have probably different personalities. They probably have different IQs. They probably have different work ethics. They're probably having a different day. Maybe Mehmet's having a good day and Aisha's having a bad day. Lots and lots and lots and lots of things may differ between Mehmet and Aisha. It could be different ages. Tons of stuff, right? So, the difference in training. So, we said Aisha got the training and Mehmet didn't. The difference with training is confounded with all of these other differences. Right? So maybe it's not that the training worked, maybe it's that Aisha had a better education than Mehmet. Right? And this allowed her, maybe the memory training didn't help at all. But because she had a better education, for some reason that helped her to do better on the memory test. She had a better test taking strategy. Does that make sense? Or maybe it's just luck. Yeah?
You change that by the random assignment.
So, something about random assignment. What's this about random assignment?
I mean, random assignment, we guarantee that there's this possibility of this difference to affect the result in general.
Yeah, so when we take a large sample, these differences should sort of cancel out on average, right? Because if you really have a truly randomly assigned sample, on average you should have equal numbers of males and females in both groups. You should have equal numbers of Muslims and non-Muslims in both groups. You should have equal numbers of people with high educational background and non-high educational background in both groups, right? So over the long run, this should tend to cancel out, right? So that's an important fact. If you remind me, maybe we can come back to this later. Anyway, Ramza, on the other hand, is Ramza, right? She's the same gender when she takes it at time 1 and at time 2, probably. Right? Same background, basically, same personality, same IQ, same work ethic, same age, same, basically everything is the same, right? So the difference in training isn't confounded with all of these differences. It was before, here for Mehmet and Aisha, it's not for Ramza. There's some other things that changed. So, you know, she takes the memory test first, and then she gets the training, and then she takes the memory test again. Well, maybe it's not the training that influenced things. Maybe it's the fact that she's taken the test twice, right? That's a possibility. Maybe it's just that the hour that it took her to do the training, in that hour she matured more, and it's the extra hours worth of maturity that did something too. But this is sort of unlikely, at least this hour explanation, right? This is a research methods problem, not a statistics problem. So we're not going to worry about that for the rest of this class. Okay, so let's talk briefly about independence and correlation. So we're going to talk about correlation a lot in several weeks. But hopefully some of you guys already have an idea for what correlation is, if you've had intro or maybe statistics in high school. What is a correlation, basically?
Relation.
It's a relationship between two things, right? So I said here, how much sets of scores vary together? This is a simple, not very precise definition that will make a lot better later, but it's a reasonable way to think about things. So as scores go up on one thing, do scores go up on the other thing, right? If they do, then you've got a positive correlation. Now, for independent samples, what should the correlation be if the samples are truly independent?
No correlation?
There should be no correlation, right? I take the first sample, maybe the best scorer in the first sample turns out to be the first person that I took in the first sample, right? But the best scorer on the second sample, they might turn out also to be the first person, but odds are probably that they're not, right? So there shouldn't be much of a correlation. There shouldn't be much of a relationship between how the first person performs in the first sample and how the first person performs in the second sample, or how the second person performs in the first and the second person performs in the second. Does that make sense? So for independent samples, there should be no correlation. So high scores for our fourth person should be just as likely to occur with a high score in our second sample scores fourth person as it should be a low score. For paired or dependent samples, though, should there be a correlation?
Yes.
Hopefully, if we have paired things wisely, there should be a high amount of correlation. For something like the example that we gave where we have Raza performing against Raza, the correlation should be very high, right? Because of all those things that aren't changing. There's a relationship, a very close relationship to Raza at time 1 and Raza at time 2, right? Some things have changed. But compared to the independent situation, things are much, much more tightly coupled together. So there should be a strong correlation, which would mean that people that got a high score in the one sample should also be the people who are tending to get high scores on the other sample, if we have a positive correlation, right? Yeah.
Should always we use correlation, positive correlation with paired samples?
No, not necessarily. You could have a negative correlation with paired samples, depending on what type of thing that you are expecting. So you would expect potentially people with lower levels of impulsiveness to have higher bank accounts, right? Because they wouldn't be as impulsive in spending their money. So we'll talk more about the difference between positive and negative correlations later. But the key here is that for the dependent samples, if we pair things correctly, there should be a correlation. And if we paired it really well, we should have a very high correlation. Whereas with independent, we shouldn't have correlation. Okay. So the data that we're going to be using, I created a set of scores in R. And I'm posting the scores online so that way you guys can download them and go through the examples yourself if you want to. So I created my first sample. I took a random sample, R norm. The population is normally distributed. This is a good thing because the t-test is based on the assumption that you're sampling from a normal population, or if the population isn't normal, you can still use the t-test when you have a sample size about 30 or more, right? Notice here, I said R norm 12. 12 here, this is the sample size. So if I wasn't sampling from a normal distribution, we would have some problems. I'm sampling from a normal distribution, no problems here. Okay, sample size is 12. I said 50 is going to be the mean with the standard deviation of 12. Then what I did is I created a paired sample by adding a set of differences. So let's look at the code that I used. So paired equals sample. So if paired just was sample, forget the rest of this, what would the correlation be? Does anyone know? If I said paired equals sample,
Positive.
there would be a positive correlation. What type of positive correlation? Weak one, strong one, perfect one?
Perfect.
It'd be a perfect positive correlation. But it's not going to be perfect because I add this other stuff to it. I randomly sampled again 12 because I have 12, the size of 12 in my original sample. And this is like the difference on the second test. So the first person here, they had their score on the first test plus some difference. And these differences are also randomly, normally distributed. Basically what I'm doing is I'm adding some random amount to each person's score, right? And the mean random amount that I'm adding is 5. So I've artificially created sample 1 with a mean of 50, and my mean of sample 2 should be about 54, right? Yes?
Can you give an example? Can you give an example with difference and the first score and the second score?
So our norm from, mean of 5 and 4, let's say we get something like 4.13. So whatever person's score was on the first memory test, their score on the second one would then be that score plus 4.13. And someone else, they got maybe negative 1.8. So they have their original score plus negative 1.8. So I'm basically just adding differences onto different people's scores. Typically when people take an exam twice, they get different scores, right? Now if the hypothesis here was that the training, well, the null hypothesis was that training didn't improve anything. The way I set things up is that the training actually did improve something. Okay?
What is 5 here?
But maybe, I didn't mean to go into R,
It's not being part of the match.
but let's go into R so we can see what I did. All right, so sample. Here's my sample. 36, 40, 40, 53, 39, 49. It's a random sample that should have a mean around 50. Mean. Sample. 45. It's not 50. We have a pretty small sample size, so the law of large numbers hasn't really kicked in yet. So no big deal. And the variance, or let's do the standard deviation of sample, should be around 10. But again, we have a very small sample size, so it's possible that it won't be that close. So 7.33. Now, that second part that I had, this R norm 12, 5, let's call these differences. Equals R norm 12, 5, thank you, 4. So let's look at our differences. So this means that the first person did 5.4 points better on their second test. The next person did 8.5 points better. The next person did 5.3 better. The next person did 2.6 better, or 2.06 better. Does that make sense? So I've basically just created a set of scores by taking the first sample and then adding some random difference to it. Okay? Okay?
Okay.
Okay. All right. So that created our paired sample. I also created an independent sample by randomly ordering the paired sample. So I used this function which you guys haven't seen before called sample. Sample is a variable name here. This is actually a function here. So the independent scores are just the paired scores. That are these scores randomly ordered. How does this make them independent? By randomly ordering them, I should get rid of that correlation. Because before, the paired score that was highest should have been one of the highest people's, should be one of the scores for the people that got the highest score on the first, right? By randomly mixing things up, it's possible that the lowest person on the first got the highest on the second. Okay? So basically destroy that correlation.
How will you go calculate sample area?
How will you calculate what?
Sample area.
Sample pair isn't calculating anything. It's just taking these and changing the order. I'll show you. So we have our, oh, I didn't do the paired. So paired equals sample plus differences, right? So if we look at paired, these are our paired scores. Notice that the first person, they had a 36, now they have a 41. Second person had a 40, they had a 48. The next person had a 40, they had a 45. So with the paired, typically they're scoring higher. Now, what I did with the sample paired, watch what happens to the order. Now instead of 41 being first, we have 48 first. That 48 was really second. And now instead of the 48, we have 45. Oh, is this? Okay, good. So if you notice here, where is it? This 51, which is now third, previously was second to last. So I'm basically mixing everything up. I'm getting rid of that correlation. We can calculate the correlation, but we'll do that later when we get to correlations. All right. Now, let's take a look at our samples. So the sample that I drew that will be in the data set that you have is not the sample. This is a different random sample with different differences because I just ran it in R. So, you know, when you take a different sample, you're going to get different values. But the sample that I use that will be online that you can analyze, if you do a summary, right, you do a summary of the data, you'll find that the minimum is 23 something, the mean is 47, which is kind of close to 50. And the max is 67, and the unbiased estimate of the variance is 154. For the paired sample, you have a minimum that's actually a little bit lower than the minimum before. Why? Is that what you're wondering? We'll see in a minute. Because we're going to let the law of large numbers kick in big time in just a couple minutes. Then hopefully you'll understand why much better. Okay, the mean is higher, right? Because we've added things to them. And the max is also higher. So we have a smaller minimum and a bigger maximum and a bigger mean. But just by knowing the minimum and the maximum, what should we expect about the variance? Probably going to be bigger. Well, it is. It is. Okay. Now, what if I looked at the independent sample, where I randomly sorted all of the values from this? What should these be? They should be exactly the same. Exactly the same. Why?
Same numbers.
It's the same numbers, just in a different order. Does that make sense? So the independent sample, I have exactly the same minimum, I have exactly the same mean, the same maximum, the same variance. All of that's the same. All right. Now, we know how to do an independent t-test. We talked about that last time, so let's do it. So if we have time, we can work through this together at the end of the class. I doubt we will have time today since there was a test before us. But if we have time, we can do it. Until then, here's what we get. This is the APA format for reporting t-tests. So what pieces do we have here? So we have this first thing, t, which is just the statistic that we're computing. If this were a z-test, we would say z, but we're computing a t-test here, t. What's this? 22.
Score?
The score? What score?
Sample plus t-score?
The sample plus the deviation? No, it's not the t-score. It's related to the sample size. So we had 12 observations for sample 1 and 12 observations for sample 2, right? It's the degrees of freedom. For an independent t-test, the degrees of freedom is the sample size 1 plus the sample size 2. Well, that's 12 plus 12. It's 24 minus 2, 22. So we have the statistic, the degrees of freedom. This is actually the t-score that we observed, so our observed t. And then this last piece, what is this?
P-success.
It's the p-value, not p-success. P-success is binomial. It's the p-value. So it's the probability that you would observe something this or more extreme given the null hypothesis. Right? Now, the actual p isn't 0.05. It's greater than 0.05. It's much greater than 0.05. But with APA, if you have something greater than your alpha, you just say greater than alpha. Okay, that's our significance level. What do? Sorry, fail to reject, right? That is bigger than alpha. We only reject if it's smaller than alpha, so fail to reject. Now, what if we did the independent test on the paired sample data? It would be the same. Why? Yalchin? Because we have the same numbers. The only difference between our independent sample and our paired sample is the order, right? So if we did our independent t-test for the paired sample data, we would get exactly the same answer. The means and variances are the same, so we get the same answer. Okay. Last class, I said that variances add, right? Here I'm saying that variances subtract. It depends. So, variance of the difference of independent means. Remember last class we were doing independent t-tests? We had independent samples, and I said that the variances added. That's because they were independent. So the variance of the difference of independent means is the sum of the variances in the samples in the long run, or for sampling distributions, which we did last time. Now, today we don't have independent samples. We have paired samples, dependent samples. So, interestingly, the variance of the difference of, this is the same, this is different, of dependent means, it's not the sum of the variances anymore. It's the variance of the first sample minus the shared variance. Shared variance. Well, remember earlier when I said the correlation is how much the two things vary together? That's shared variance. So we should have a lot of shared variance in our paired sample, and not very much shared variance in our independent sample. Okay, so it's the variance of the first minus the shared variance of the second plus the independent variance of the second. An example using huge sample sizes to allow the law of large numbers to kick into gear should be helpful. Alright, so let's take some really big samples. So here I have BS for big sample. Big sample 1 is equal to our norm. We're going to take a sample size 10,000. 10,000. With the same mean and standard deviation that we used for our small sample. Okay? So what should the variance of BS1 be? So our population has a standard deviation of 10. So what's the standard deviation of, or what's the variance of the population? 100, right? 10 squared.
Yes.
Now, what do we know about the law of large numbers? When we have large numbers, our estimates of the population variance are going to be closer to what the population variance actually is, right? So what should the variance of BS1 be, of our big sample be? It should be pretty darn close to 100. Okay. So, in R, before we did those examples before class, I loaded up this. So BS1, big sample 1 equals R norm 10,000, 50, 10. So, it's already there. Let's see what that is. Var. This will give us our unbiased estimate of variance. BS1, wow, 100.7. That's pretty darn close to 100, as it should be, right? All right, so our BS2P, so this is our big sample 2 that's paired. Paired, is BS1, just these scores plus some differences. Now here I have 10,000 differences as opposed to 12 differences, but same mean and standard deviation for the differences, right? So now the question is, what should the variance of BS2P be? BS2P be? That's what I say. The variance should be 8. 116? Are you some genius? How do you know that? He guessed right.
Because the square root.
So, before we said that variances add, right? And a minute ago I just made this claim about whether it was independent or dependent, right? Now, so we are adding, well actually, this, the variance in this should be independent from the variance in this because it's a different random sample, right? So all this should be is the sum of the two variances. So the variance of this should be close to 100. The variance of this should be close to 16, twice the standard deviation. So the variance of this should be very close to 100 plus 16. So, let's see if it is. All right, so here you see my BS2P, which is just BS1, BS, plus the differences, so var BS2P, woo, 116.99. That's very close to 116, right? This is a finite sample, it's not infinite, so of course we're not exactly on, but it is darn close. All right. Finally, our independent sample. Just like I did before, I'm just going to randomly order my paired sample. So what should the variance of this be? Same? What, 100, 116? Should be 116. It should be exactly the same variance as our paired data because we have exactly the same numbers, just in a different order. So that's exactly right. So it should be, again, close to 116. So var BS2I. Boom! Well, it's exactly the same as it was before. Good intuition. All right. Now, the difference between means is the same as the mean of differences. So you're just adding things up and dividing them. So you can take differences between means, or you can take means of differences and come up with the same answer. This is going to be useful for what we're going to do next. So let's get differences. So I'm going to get the big differences between my independent and the original sample, okay? So all I'm doing is taking my original sample and subtracting the independent scores from them, okay? So that will give me my big differences for the independent. What should the variance of this be?
Minus 16.
116?
Minus 16.
Minus 16. Anyone have any different predictions? So what you did is you took the variance of this, which is 100, and subtracted the variance of this from it. What did we learn in last class when we had independent samples and we subtracted one of them from the other? What was the variance of the differences? Or what was the variance of the sampling distribution of the difference between means?
The mean differences?
What did I say last class? Did I say differences add or differences subtract?
Add.
I said differences add, and we were talking about independent samples there.
Yeah.
We're talking about independent samples here, so what should happen?
Add.
The differences should, or not the differences, but the variances should add if what I said is correct, right? So what should the variance of this be if these variances add? 216, right? So they're independent samples, so the variances should add. So it should be the variance of BS1, which is close to 100, plus the variance of BS2I, which is close to 116. All right. Let me make sure I have it. Yep, BDI equals BS1 minus BS2I. So let's get the variance of BDI. 221. It's not exactly 216. Why? Because we have randomness. There is probably some small correlation in these data because we have a finite sample size. We haven't went out to infinity yet. If I took a much larger sample, I should get something much closer. Yeah. Okay. So, we saw that our big sample differences from the independent samples was indeed pretty close to 216. It was farther away than what we had when we were just dealing with one. It was still fairly close. All right, so now let's calculate the differences. So this is our big differences between the paired samples. So we have our big sample one minus all of the paired observations, right? What should this variance be? You're going to subtract down? Go ahead, subtract. 100. 100 minus 116, so negative 16. Is that right? What? Not 216, no. Not negative 16, not 216. What did you say? 16. How did you know? I mean, it's not going to be. We have a finite sample size, but it should be fairly close to 16. How did you know this? She just guessed. You know, brilliance. It's uncontrollable. She's so smart, she doesn't even know. All right. Why? Well, earlier when I said the variance is subtract, I said when you subtract paired samples, you have the variance of the first minus the shared variance of the second, right? I didn't say minus the variance of the second, I said minus the shared variance of the second, plus the unshared variance, plus the independent variance. So it should be very close to 16. So we have the variance of our sample 1, which is close to 100. Our shared variance in the paired, well, all we did was add these random differences onto that, right? So all of that other difference, or not all that other difference, all of the variance except for the variance of these differences is shared, right? So we have close to 100 minus the shared variance for our paired samples, which should be close to 100, plus the unshared variance, which is just the variance of the random differences that we picked out. So it should be close to 16. So bar BDP, bar BDP. Yes, thank you. Wow! That's very close. Good job. All right. So, hopefully that helps demonstrate what I said earlier. That when you subtract the independent samples, you add the variances together. When you're subtracting paired or dependent samples, you are subtracting that portion of the shared variance. So you'll get something that's less. Think about the intuition behind what we were talking about earlier when we were saying comparing Ravza to Ravza. So Ravza's score is whatever it is for lots of reasons. It's because of how smart Ravza is. It's because of how hard she worked. It's because of how awake she is. It's because of how much time she spent thinking about the problem. It's because of the amount of caffeine that she had. It's because lots and lots of things, right? Now that second score, all of those things basically should be the same. So all of those sources that contribute to variance in scores, we should be able to suck those things out by subtracting Ravza from herself. We're subtracting out everything, hopefully, except for the thing that we're interested in. This is a flawed design because she takes the test once, she takes the test again. Not the best research design. So there's a problem potentially with that. Like I said, that's a methods issue. Okay, so, woohoo! An important note. Here we are dealing with finite sample sizes. Even with a sample size of 10,000, this is still finite. So when we say that the variance is add or subtract, like we're talking about the long run. We're talking about the sampling distributions. So the variances of our differences for finite samples aren't going to exactly equal the appropriate sums or differences of the parts. So for an example, we said the variance of BDI should be equal to the variance of the initial set plus the variance of the paired second set, right? So if we do that, right, this should be BS 2I. So our var BDI was this. Our var BS1 was this, and our var BS2I was that. If we add these things together, which is what I said should happen, notice that we got 217, which is actually different from the 221. Why? Because it's a finite sample, and there's some small amount of correlation in the data. All right. Let's get back to our small sample example. I like how that went. Small sample example. All right. One sample t-tests are like honey badgers. You guys seen the honey badger video on YouTube? Okay, after class. You will have other homework, but for homework, go to YouTube and type in honey badger. It is hilarious. So the honey badger doesn't care. The honey badger is tough. The honey badger wants honey. And the honey badger goes to get the honey, and there are all these bees stinging the honey badger. Honey badger don't care. Honey badger is hungry. Honey badger wants some meat. Well, there's a poisonous snake right there. The poisonous snake bites honey badger. Honey badger don't care. The one sample t-tests, they don't care. As long as the population is normally distributed or the size is large, you can analyze lots and lots of stuff. You can use them for number of items remembered, a memory test. You can use them for millimeters of mercury. You can do them for heights, weights, IQs, whatever you want. As long as you have this basic assumption there. Now, we just demonstrated that differences get rid of the shared variance. So we could do a t-test on the differences, which should decrease the variance. Now, the t-test, remember the one sample t-test, we have the standard error of the mean in the bottom, right? The standard error of the mean is dependent on the variance. So if we can make that variance really, really small, that'll be good. That should make our t big, because the standard error of the mean is on the bottom. So if we make that small, t should get big. And the bigger t is, the better chances we have of rejecting it, right? For some given sample size. So let's use the difference scores for our paired samples. Do a paired t-test. Basically, our paired t-test, this is why I said it's old. Our paired t-test is just a one sample t-test. But it's on differences. So we can rewrite the null hypothesis as the mean difference is 0. Right? That's equivalent to what I said before, which is the mean of test 1 minus the mean of test 2 equals 0, right? Mean difference, 0. Okay, so we've got our null hypothesis. All we have to do is subtract sample 2 from sample 1. And I already showed you guys how to do that. You can just say sample 1 minus sample 2, and R will take care of it for you. All right, then we can do a one sample t-test of the differences. Oh, shoot. Okay, so the paired difference analyze the data yourself for the thing that I'm going to put up on the internet for you to see that the minimum is -9, the mean is -4. It should be close to -4. We said that sample 1 should have a mean of 50, right? When I said randomly sample, take 12 samples from a mean of 50, right? And then that second sample was the first plus, on average, 4. So we see -4. The unbiased variance is 11.7, which is close to 16. It's not as close as our previous estimate was because we don't have as large of a sample size. All right, how many degrees of freedom do we have for this?
10? Is the degrees of 10?
Not 10,
12, 11.
11. You said 22, someone over here?
Nice.
11, 22. One of these answers is correct. Which is it? 22, 22? Show of hands for 22. How many people say 22 is the correct one? How many people say that 11 is the right one? All right, fewer of you guys say that 11 is correct. So why don't you guys tell me why 11 is correct, if you think that that's right?
Sample size was 12.
Sample size is 12.
The degrees of freedom? 12 minus 1.
12 minus 1, but no, we have two samples, right? A sample size 12 and a sample size 12. 22?
22, yeah.
The people that said 11 are correct. Or they were correct until they changed their mind. Why are they right? What are we analyzing here? We're analyzing differences, right?
But,
How many differences do we have? We have 12 differences, right? We had 12 observations in sample 1, 12 observations in sample 2. Well, if we were doing like the independent t-test, then we would have 24 observations to go off of. We're estimating 2 means, so we need to throw away 2 of those degrees of, or 2 of those observations for our degrees of freedom, and we would have 22. But here, we're not looking at the observations against the observations. We're just looking at the differences. There are only 12 differences. So, just n minus 1, 11. What's the standard error of the mean?
square root of unbiased variance divided by n.
Ding, 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 ding. Yes, that's exactly correct. Okay, so that's exactly right. So, now our pure t-test. We have our mean from before, we have the degrees of freedom, and we have the standard error of the mean, right? We have the information that we need to compute t, right? So, how do we compute t?
Mean.
T equals -4, the mean,
Minus 0.
minus 0, our predicted mean difference, right? Okay, good.
Divided by standard.
Divided by the standard error of the mean, so 0.98 and change. So our observed t-score, yeah, that's exactly right. Boom. It's -4.05. Now we need to find the critical values for t. We use qt to do this. You have alpha of 0.05. So we can do qt 0.975 with how many degrees of freedom? 11 degrees of freedom. And that will give us our upper critical t value. And then our lower one is just the negative that, right? So our critical t's are plus or minus 2.2. What do we do?
Reject.
We reject the null hypothesis. Yeah, we reject the null hypothesis. Awesome. Now what if? What if? What if we took the differences of the independent samples and ran a one sample t-test on those differences? Right? So we have independent samples, 2 groups of them. What if we did the same thing we did for the paired samples here?
Paired samples are dependent.
The paired samples are dependent, but what if we took our independent samples and tried to treat them like this?
We should add variance. You said.
We would be adding variance actually, right? If we're going to take the difference of those 2 things, then what should happen is that variance, the standard error of the means, should actually end up getting much larger. Now, the mean is going to be exactly the same. And the variance of both of those pieces are exactly the same, right? Because we're dealing with the same data. But the standard error of the mean, when we create that, we're going to be adding those variances together. So the numerator should stay the same, that is the -4, but the denominator should be much bigger. So, oh my goodness, you're exactly right. So the variance before was like 11 something. Here it's 281. The mean, exactly the same. Maximum, exactly the same. Minimum, exactly the same. I'm sorry, that's not correct. The mean is exactly the same. I was thinking about the minimum and the maximum for just that second part, but this is the difference. So the difference, right? The variance is bigger, so we would expect that the minimum and maximum should be potentially bigger than they were before. Let's go back and see if this is right. So we have -30 up to 20. -9 up to 2. So the minimum is much lower and the maximum is much higher, which explains why we have a higher variance. All right, so the standard error of the mean, that's just square root of 281
0.65 divided by n plus
divided by n, which is 12. Still dealing with the same sample size. So before it was like 0.9874. Now it's much bigger, 0.484. So we had the mean before, which is the same as it is now. -4 divided by 4.4. This is going to be less than 1, right? So our observed t-score, -4 divided, sorry. -4 divided by 4.84, Gibby, 0.823. So I got this part right, I got that part wrong, 4.84. All right, so our observed t-score is -0.83. It's really tiny. What was our critical value?
minus and plus 2.20.
Is it going to be the same thing here? Yeah, it's going to be exactly the same thing here. The critical values aren't changing because the alpha isn't changing and our degrees of freedom aren't changing. So the critical values are going to be exactly the same. What do? We have to reject. Good. All right. Now, before when we did our independent t-test on the independent samples, we also failed to reject, right? Why don't we always just take the differences and run the test on those? Some people might say, like, the test on the differences is easier, right? Why is the test on the differences easier? Well, you don't have to compute that pooled estimate of variance, right? That was sort of a pain in the butt for the independent t-test, right? Okay, let's assume that the variances are equal. Now we're going to pool the variances. So n-1, or n1 minus 1 times variance estimate of the first plus n2 minus 1 times the estimate of the variance for the second, all over n1 plus n2 minus 2, right? And that gives you a pooled estimate of the variance. So you don't have to do that here. You don't have to compute the standard error of the difference between means. You just compute the standard error of the means. Well, the logic behind taking the difference is to get rid of that shared variance. By getting rid of that shared variance, you are decreasing the denominator. As you pointed out earlier, if you don't have much shared variance, you're going to be increasing the denominator. This will make it harder for you to reject. If you're not getting rid of anything, there's maybe no point in doing it. But if you are getting rid of something and the samples really are independent, then you're just basically taking advantage of chance. That the samples were slightly correlated because of chance, right? You also lose degrees of freedom. So if you make the variance on the bottom bigger and you lose the degrees of freedom that you have, you're going to make it much, much harder for yourself to detect a true difference. You're going to lose power. Okay, this is a good trade-off when you can get rid of shared variance. Not such a great idea otherwise. So, okay, let's take a look at using the independent and the paired t-tests on the independent data. So, this stuff up on top, this is what we had at the beginning of the class. I said that the p was greater than 0.05. Was a lot greater than 0.05. This is 0.4836. Now, for the independent t-test, does the order matter? No. For the independent t-test, order doesn't matter. And we demonstrated this by using an independent t-test on the paired data. And we got exactly the same answer, right? So these values here are going to be identical for the same data, regardless of the order that you put that data in. However, for the paired t-test, this isn't necessarily true. The t that you observe and also the p-value of the t that you observe, these are going to change for the different orders. So you get one order and it happens to be a lucky order, you might end up projecting the null. Let's take a look. Let's do some different orders. So I did some R code and I did a whole bunch of t-tests on exactly the same data. I just changed the order by using sample. Sample, that independent stuff. I got a new order for the same data. So, p-value of 0.6, p-value of 0.45, 0.5, 0.45, 0.53, 0.53, 0.50. I have some down here, 0.37, 0.34. So the p-values and the t scores that I'm getting differ. Why? Because when I randomly order things, with a finite sample size, there are going to be some small correlations in that data. And if we get really, really lucky, we might have something that we might end up rejecting when we shouldn't. So about half of these are greater than what we got for the independent test. Occasionally we'll get lucky and capitalize in chance. In statistics, what do we try to do? We try to rule out chance, right? We want to figure out whether there's an effect or not. What do? We use controls. We use sampling distributions. And we say, okay, just by chance it should be this far away. We're trying to account for that chance and rule it out. We're only saying something is significant if the chance of it happening when the null is true is really, really tiny, right? We're trying to limit chance, not capitalize on it. So you shouldn't use the paired t-test if you don't have a natural pair. What's a natural pair? Rabza and Rabza is a natural pair. What are other natural pairs? Sibel and Sibel. William and William. Yes, those are natural pairs as well. What other things? I said something about Rakesh. Rakesh is getting married. You could use spouses as a pair, right? Why do people get married to one another? Well, if they have a choice in the matter, even if they don't have a choice in the matter, there are things that are similar enough, right? Our views are similar on this. We get along in that way. We get along in this way. Yes, it's a pair, right? What other things could you use to pair? Spouses? Twins. Twins are great pairs, especially what type of twins? Identical twins are great pairs. Then we don't have to worry about this whole getting the test twice problem. Right? Give one twin the test once without the training, the other twin the test with the training. Totally get rid of that issue that we had from my poor design. What else? It's easy, easy.
Wait, siblings.
Siblings. How about students? If we wanted to pair students together, how could we do it? Non-sibling students.
Same IQ.
Same grades. So we want to give tests to people. So we get a random sample of people, and then we sort them by grades, by GPA. Because we would expect people with higher grades should have higher memory scores, right? Does that make sense? So what do we want to do? Okay, we'll take the people who got the highest grade, and we'll flip a coin to determine which one goes into the training group and which one doesn't. And we'll take the next two people, and we'll do the same thing. Flip a coin. And what should happen? Well, now the person with the highest score is paired with the person with the second highest score, and vice versa. So you have this sort of natural pairing of things. You can use lots and lots of stuff. You can use the same person. This is called repeated measure, and this is my favorite way to pair information. Siblings, roommates. Your roommates in the dorms, they are natural pairs. People that scored similarly on some different measure. What we do not want to do is pair people for their performance on the measure of interest. So we take a random sample, test their memory, take another random sample, train them, test their memory, and then say, oh, well, let's pair the highest person on this with the highest person on that. And the lowest person on this with the lowest person on that. Why? The samples were independent. There shouldn't have been a correlation. By pairing them like that, you artificially introduced a correlation. Correlation that wasn't there. You made one. And this is the most extreme way to capitalize on chance. If we had two samples, and I do, for the data that I've been talking about, I can sort them. Or you can use this function called sort to sort the data. So I used a paired t-test on the independent data, and I sorted both of them. So the lowest went with the lowest, and the highest went with the highest. And we got a t negative 0.5, p-value 0.0002. This is actually much more extreme than our paired test was. Because we took advantage of this artificial pairing to increase the correlation in our data and get rid of more variance on the bottom, which will inflate our t. So if you ever do a paired t-test. Do it on some pair that doesn't have to do with the thing that you're testing. Do it on something else. Really? Alright, so when you have a dependent sample that is paired, all you need to do is subtract one member of the pair from the other. For the homework, subtract the second from the first, and you'll get the same answers I do. Otherwise, if you subtract the other way around, you'll get the negative version of that. And then do a one sample test on the differences. The paired t-test is just a one sample test on differences. Old questions. Old tests. Different thing that we're analyzing. That's it. Next class. ANOVA.